All right, so 4.6, modeling with exponential and logarithmic functions. Our learning objectives are we are going to find exponential models of population growth, decay, Newton's law, cooling, that's my favorite, and compound interest. Okay, so let's look at this first one, and it's going to be for doubling time. So it's basically, if they tell you how long it takes a population to double, then you're going to be using this formula. So N naught is the initial size at population T, and A is the time to double. So we kind of did something like this in previous notes where we started and said how long or what would we put in for the rate if it's going to double, and we put the +1 because we're going to be getting itself again. Well, if you see 1 plus 1 would just give me the 2. So let's look at this first example. A certain culture of the bacterium Rhodobaga sapphire, something like that, initially has 25 bacteria and is observed to double every 5 hours. Find an exponential model with the doubling time formula for the number of bacteria in the culture after T hours. All right, so this one told me that it had an initial amount of 25, so I can put the 25 in. I'm going to use my 2 for the doubling. And it says that it's going to double every 5 hours. So I can put in my 5. B then says, estimate the number of bacteria after 18 hours. So I'm going to put in 18. And you can put that in your calculator, and that's about 303 bacteria. See, after how many hours will the bacteria reach 1 million? So now I'm going to set it equal to 1 million. So the first thing I need to do is divide by 25. And now since I have a variable up in the exponent, I'm going to ln both sides. That would bring my exponent down. Now I can multiply by 5 and divide by the ln of 2. To get T. So you can see what that is approximately by putting it into your calculator. And I got about 76.4, and time here it said was in hours. Let's try another one. A certain species of bird was introduced in a certain country 25 years ago. Biologists observed that the population doubles every 10 years, and now the population is 13,000. A wants to know what was the initial size of the bird population. So I know right now it's 13,000. I do not know my initial size. It was 13,000 25 years ago, and they told me it doubles every 10 years. So now basically I just need to solve for N naught. So I can divide both sides by 2 to the 25th tenths, and that would give me my initial size, and that would give me approximately 2,298 birds. estimate the bird population 5 years from now. So the first thing I'm going to do is rewrite my formula now that I know my initial amount. So there's my general formula. And 5 years from now would be the 25 plus the 5 that I will have to put in. Because we had 25 years ago, so 5 years from now I can put in 30. And this gives me approximately 18,384 birds. Okay, let's look at the next one. So with exponential growth, we've kind of seen this. This is just our PERT. The initial amount, E means it's growing continuously. R is the rate, the growth rate, and T is the time. Now, whenever we're dealing with money, time has to be in years. But if we're dealing with anything else, we can have time be in minutes, hours, seconds, days, whatever they tell us in the problem. So, example, the population of a certain species of fish has a relative growth rate of 1.2% per year. It is estimated that the population in 2000 was 12 million. Find an exponential model for the population T years after 2000. So they told me that the initial amount was 12 million. The rate was 1.2%, and T is the general time in years, or time in years? Yes, in years. So let's see, for the population after 2000 then, I'm going to have to put in a time of 5 for 2005. And here I got approximately 12,742,039 fish. Okay, and C, after how many years will the fish population reach 14 million? So I'm going to set it equal to 14 million. So I can divide by 12 million. ln both sides. Which means that's going to come down in front. And the ln of E is just 1. So now I can divide by 0.012. Which would give me approximately 13 years. And D wants me to sketch a graph. So I have time in years, and the population of fish. And we can write this in millions, so I don't have to write all those zeros over and over. I'm going to go by 2s. I know that the initial amount was 12 million, and you could really have your time grow as much as you want by 10s, by 1s, by 30s, but it's going to grow up this way. All right. The bat population in a certain Midwestern country was 350,000 in 2009. And the observed doubling time for the population is 25 years. Find an exponential model with the doubling time formula, T years after 2006. So there's my initial amount. doubling, so I'm going to have 2 raised to the, and they said it doubles every 25 years. B says find an exponential model for the population t years after 2006. So now I'm going to use the same information but write the exponential model. So I know that I had 350,000 to start. And then they told me that after 25 years it would be double. So double meaning I would be at, oops, sorry about that. After 25 years. So now I can solve for R. And I got the ln of 2 over 25. So I know my formula would be 350,000 e raised to the ln of 2 over 25 times t. Okay, part C says estimate how long it takes the population to reach 2 million using both part A and then using part B as well. So we're doing part C, and let's use it with part A first. What do you think is going to happen here? I have 2 different formulas going on. But if I'm asking a question, hopefully we're going to get the same answer. Let's see. All right, so solving for t, I got that big old blob, which is approximately 62.86 years. Let's see if we did the same thing with B. All right, so plugging in 25 here and solving, I'm still going to divide first. So I'm going to ln both sides. Ln of e becomes 1. So solving for t, I get 25 ln of 40 over 7 divided by the ln of 2. And what do you know? They are the same answer. Yay! So this, again, is approximately 62.86 years. And you can scratch off t. Okay, radioactive decay. So it's going to decay, and I'm given this formula. So here, this is our initial, here's our rate and our time. If it tells you a half-life, then you can find your rate by doing the ln of 2 divided by the half-life. And this example is a little bit off. I'm going to go ahead and switch it so you can fill in. I accidentally did the wrong one here, I think. So this should be a 10. And I want this to be 80. So it's similar to a homework question that I assigned, so I want to make sure I get to the right. And instead of 18, we're going to put 2. again, this can't hardly see is 80. All right, so let's do part A. Find a function that models the mass remaining after t years. And they told me the half-life. Okay, so my initial amount is going to be the 10. So right here I have the 10 for my initial amount. I have 2 raised to the negative t over 30. So let's go ahead and see what they want me to do next in part B. Find a function that models the mass remaining after t years when I'm given the equation right here. So again, my initial amount was 10. And now I'm going to have e raised to the negative. And for the rate, I have to fill in the ln of 2 divided by the half-life of 30 times t. Okay, so part C says how much of the sample will remain after 80 years in part A and in part B. So let's plug in 80 for both of these. And again, what do you think will happen? Let's do the part A first. So I got about 1.57 when I plugged it into A. And then plugging it into B. I got the same answer. Yay! So it's just showing you there's lots of different models that you could set it up that would give you, it would demonstrate what's going on just the same. So it's a good representation either way. All right, D. After how many years will only 2 milligrams of the sample remain in part A and part D? So let's do it with part A. So I'm going to divide by 10. ln both sides. And I got t to be negative 30 times the ln of 1/5 divided by the ln of 2, which is approximately 69.66 years. All right, if I wanted to do it with part B, still going to divide first. ln both sides. ln of e is 1. So solving for t. We get the same answer. Pretty cool. All right, now my favorite, Newton's law of cooling. A lot of you are going to love this one. So here, Newton's law of cooling is going to be given by our formula. T of t equals T of the surrounding temperature plus the difference of the temperature raised, or times E raised to the negative KT. And K, like, has been scientifically proven after lots of experiments for whatever they're giving you. So it's going to be some positive constant, and they'll give you that. All right, so Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees Fahrenheit. Immediately following death, the body begins to cool. It has been determined experimentally that the constant Newton's law of cooling is approximately 0.1947, assuming that the time is measured in hours. Suppose that the temperature of the surroundings is 60 degrees Fahrenheit. Find a function t that models the temperature t hours after death. All right, so my surrounding temperature is 60, plus the difference would be the body temperature minus the surrounding temperature times E raised to the, they told me K was 0.1947 times T. Okay, so you ready for the cool part? If the temperature of the body is now 72 degrees, how long ago was the time of death? So I can set 72 equal to this formula. Go ahead and simplify those parentheses. So I'm going to subtract over the 60 first. Divide by 38.6, and I went ahead and math fracked it after I did that division. ln both sides. And divide one more time. Which is approximately 6 hours. So you know that this body died about 6 hours ago, just from this. Pretty dang cool. All right, so there we go. Have a good night.